In this video, we're going to talk about spectroscopy, which is all about the interactions between light and matter. And when we're talking about light, we're not just talking about visible light. We're talking about electromagnetic radiation in general. And so what I'm going to do to give us an intuition here is use the PhET simulator by the University of Colorado. I encourage you to go to this URL and try it out for yourself. But you can see what the simulator does is it allows us to essentially see how different wavelengths of electromagnetic radiation can interact with matter, in this case, various molecules. And just to get our bearings, we can click on this light spectrum diagram. And we can see that on this diagram, what people would normally consider radio waves, these are some of the lowest frequencies and longest wavelengths of light. And then when you get to higher frequencies, you get to microwave. And the higher the frequency, that's also the higher the energy per photon. And then you get higher frequencies than that and higher energy, that's infrared. And then higher frequency and energy than that, that's visible light. That's what our eyes can sense. And then you get even higher frequency and more energy. You get to ultraviolet, then X-ray, and then gamma rays. And this isn't a linear scale. You can see that this is a logarithmic scale here. This is in powers of 10. So we see some pretty dramatic increases in frequency and energy as we go from the left to the right. But in this video, we're going to focus in particular on microwave, infrared, visible, and ultraviolet wavelengths of electromagnetic light or electromagnetic waves, and think about how they interact with molecules. So if we start with microwave radiation, and here we have a water molecule, I've picked that right over there, and I can get my simulation going. You can see what it's doing is when it gets absorbed, it causes a rotational transition in the water molecule. It makes the water molecule rotate in a different way than it was before. And then the water molecule can also emit the radiation and then rotate differently. And so you can see it doesn't always do that. There's a little bit of probability involved. But this is actually the basis of how microwaves work. Your microwave oven is it causes the water molecules to get agitated in a rotational way, which increases the heat in that system. Now we could also look at infrared light, which is, once again, we have to remember, gets us into higher frequencies, and see what that does to molecules. So based on this simulation, it looks like the infrared light is when it gets absorbed, it causes this water molecule to start to vibrate. So microwave radiation caused it to rotate or to have a change in state of its rotation, while infrared makes it vibrate. And we can see that with other molecules as well. Let's try carbon monoxide. Once again, it's not rotating it, it's causing it to vibrate. Now what about visible light? Well, visible light will have different interactions with different types of molecules, but let's try it out with nitrogen dioxide. So there's certain situations where nitrogen dioxide will absorb, that's when you saw it glowing. And what you see when it's glowing, what it's really doing is it's putting electrons into a higher energy state or into a higher orbital. And then when it stops glowing, it means that those electrons are going back to a lower energy state. They are re-emitting radiation. So there you can see it. You can see that just now it's re-emitting visible light, in this case a different direction. And when it did that, the electron that was excited went to a lower energy state. Now what about, let's think about ultraviolet light, which has even higher energy than visible light. What can that do? Well, here we can see that it takes, in certain cases, electrons, and it's able to excite them so much that it's able to break that bond itself. And so let me keep resetting it. So you can actually break bonds. Let's see what it can do to some ozone. Same thing. It excites it so much that it can actually break the bond. It's exciting an electron so much. I can keep resetting it. So the big picture here, the big takeaway, you could have microwave radiation, which tends to change the rotational motion of a molecule. We saw that with the water molecules. You have infrared radiation, which is higher energy and higher frequency, which tends to lead to a change in vibrational motion. And then you have visible light, which can excite electrons, take them to a higher energy state, and then be re-emitted when the electron goes back to its base state. And then you can have ultraviolet light that's so powerful it can excite electrons so that in some cases it can even break covalent bonds.
Say we could also measure the wagging. And let's happen to say that it wags at 4 hertz, which again, it means it goes back and forth one cycle, or wags back and forth, 4 times per 1 second. If that's the reality, then let's see what happens when we take our formaldehyde molecule and we stick him in the IR spectrometer. And let's again label our stretchings at 2 hertz and our waggings at 4 hertz. So here is how the IR spectrometer functions. What happens is when the molecule is in the machine, we take something like this, a light source, which is simply something that has the ability to shine light at a molecule at various frequencies. On the other side of the machine, we have this thing right here, a detector. And all he can do is detect light. Now, imagine this for a second. Let's say again, our light source has the ability to produce light at various frequencies. So let's say we set our light source to deliver a light that happens to have a 1 hertz frequency. If we shine this 1 hertz frequency light at our molecule, it'll go right through the molecule and hit the detector. And the detector, of course, would say, when you shine 1 hertz frequency light at the molecule, I detected it. We'll see why that happened in a second. But for now, let's graph what we see in front of us here. If you had a graph with, let's say, on the y-axis, the percent transmitted, and this means the percent of light that transmits or moves through the molecule, which would obviously run from 0 to 100%. And let's say for now on the x-axis you put the frequency of light. So the graph of what we just saw here would look like this. At 1 hertz frequency light, 100% of the light went through the sample and the detector detected that light. Now, let's see what happens if we go back to our light source and now let's set it at 2 hertz frequency light. If we shine this at the molecule, what's going to happen here is the molecule will actually absorb light at that frequency. And this right here is key to understanding how this machine works. Notice the frequency of the light that's being absorbed, 2 in this case, matches the frequency of the stretching. When these two things match up, the molecule will absorb the light, which means think about the detector here. His observation is that when you shine 2 hertz frequency light, he doesn't detect the light at all because it was simply absorbed by the molecule. Let's see what this would look like on our graph now. Again, at 2 hertz frequency light, the detector would say not very much transmitted through it. A lot of it was absorbed. So we have a small percent that's transmitted. And that would be this point on the graph. Now let's go back to our machine here. Let's now take our light source and set it at this time 3 hertz. Think about what we just learned here. If this molecule stretches at 2 hertz and wags at 4 hertz, then when we shine the 3 hertz frequency light, it should go right through it. There simply is no match in this case. And the detector therefore would say 100% of the light transmitted through the molecule. So again, going back to our graph right here, we would see that this would be the graph at 3 hertz frequency, 100% transmitted. Now while we're here, let's do this. Let's connect these dots. This is what we would have. However, let's go back to our IR and let's talk about one more case here. What if we set the light source this time to 4 hertz frequency light? If you've been following along, since this molecule does wag at 4 hertz, then we should expect this light to be absorbed by the molecule. But just to let you know, in some cases, not all of the light is absorbed. And let's just pretend for this case, even though it wags at 4 hertz and it does absorb the 4 hertz frequency light, some of it actually does eventually get through. This happens sometimes in the IR, which means, let's go back to our graph here. If we were to graph this point at 4 hertz, let's say this much percent passes through, which means we would get this point on the graph. And again, let's connect these dots. We'd end up with something that looks like this. What you're seeing here in front of you is basically what the IR machine spits out when you put a sample molecule in the machine. And the vocab here is this. We would call these simply absorption bands. Think about where that term is coming from. It is at these points that light is being absorbed by the sample molecule in the machine. And think about what this means for us. Remember, all carbons and oxygens are the same, and all carbons doubly bonded to oxygens are the same as well. This means that if any sample we put in the IR machine, as long as we run it, let's say, at room temperature, and if the molecule happens to have a carbonyl group, it's going to stretch and wag at 2 and 4 Hertz, no matter what molecule it happens to be in. Which means this: if we do run a sample molecule through the IR and we see absorption bands at 2 and 4, we're going to know without a doubt that our molecule has a carbonyl functional group, because it's only carbonyls that stretch and wag at those particular frequencies. For instance, it's safe to assume that, let's say, if the carbon were singly bonded to the oxygen, remember, single bonds are longer than double bonds. So you can think of that single bond as being a different type of quote-unquote spring than the double bond, which means if your molecule had a C singly bonded to an oxygen, that bond would stretch and wag at different frequencies than the C double bonded to the O, and would therefore have its own unique absorption bands. So notice what the IR helps us figure out. It simply helps us determine what functional groups that might be present in a molecule. However, let's look at an actual IR spectrum. This right here is the real deal. Notice on the y-axis here you do have the same thing, the percent transmitted. And notice we also have absorption bands that look like this. Sometimes they're broad like this here, sometimes they're narrow, and sometimes they're, well, in between. But what I want to point out here is that in the actual IR spectrum, they don't put frequency on the x-axis, they put wave number instead. There's a good reason for this, but it's beyond this lecture at this point. Just know for now that there is a connection between frequency of light and wave number of light. And instead of thinking that absorption bands happen at certain frequencies, we can say absorption bands also happen at certain wave numbers. And just in case, let's know these wave numbers typically on the chart run from 4,000 all the way to 0. Some other basics about the IR spectrum here. Let's know that right about here, from 1800-ish to 4000, is what's called the functional group region. This is where we're going to look for absorption bands that signal certain types of functional groups in the molecule. And the other side of this region right here is called the fingerprint region. We're going to see that certain molecules have certain absorption bands in this region, and those bands can act almost as fingerprints, meaning that every type of molecule in organic chemistry has a specific fingerprint region with its corresponding absorption bands that are unique to that molecule. Now remember here, the whole basis of the IR machine, again,
Hello, I'm Luis Serrano, and in this video we're going to learn Principal Component Analysis, or PCA. Principal Component Analysis, or PCA, is one of the most important dimensionality reduction techniques out there. What is dimensionality reduction? Well, let's say you have a huge table of data, so big that it's hard to process, and you would like to make it into a smaller one while still keeping as much of the information as possible. So dimensionality reduction techniques, what they do is they reduce the number of columns. So today we're going to learn PCA in a few steps. First, we're going to learn what projections are. Then we're going to learn variance, covariance, the covariance matrix. Then we're going to learn what eigenvalues and eigenvectors are. And finally, we're going to go to PCA. So let's begin. So let's start with a simple problem. Let's say we have a bunch of friends standing like this, and we want to take a picture of them. So the question is, where do we take the picture from? What angle? So it could be this one, it could be this one, or this one. Well, it seems like this would be one of the best angles to take the picture, right? And that's really what dimensionality reduction is. It's taking a picture of your data and trying to keep as much information as possible in this picture. So when your data looks like this, then a picture of the data could be, for example, projecting it over this line. Then you get these points over here. Another one could be projecting it over this line. Now the question is, intuitively, which of the two projections seems better? Let's compare them, put them side by side. Well, it seems to me that the one on the right is better because the points are more spaced out and you can actually tell them apart. If you only had this picture, you could actually make out the data a little better than with the one on the left. So what we're going to learn in this video is how to obtain the projection in the right, how to get that sort of ideal line to project our data and keep it as sparse as possible. So first, a little parenthesis. Why does this matter? Why do we do this? So let me give you an example of some housing data. Let's say we have a housing data set with a bunch of columns with the following information: size, number of rooms, number of bathrooms, the schools that are around the area, and the crime rate. So if I gave you this data set and I told you there's too many columns, there's 5 and I want less, what would you think? Feel free to pause the video and think. How can we sort of reduce this and keep the information? Well, just from eyeballing it, I can see a difference here, right? The first 3 features are related to size. So maybe we can lump them together into something called a size feature. And the second 2 are related to the neighborhood. So let's lump them together into something called the location feature. So that's what dimensionality reduction is, right? We went from 5 columns to 2. And we're capturing the information because it seems to me that a bigger house may also have a higher number of rooms and a higher number of bathrooms. So we may not need the 3 pieces of information. We may need maybe a sum of the 3, or maybe a weighted sum. And the same thing for the second, for the location feature. So how to do this ideally? That's what PCA does. So let's look at an example, not from going from 5 columns to 2, but let's go from 2 columns to 1. So we have number of rooms and size, and we're going to try to lump those into one feature. So we have a graph here where on the horizontal axis we have number of rooms and on the vertical axis we have size. And notice that our suspicion was correct. The bigger the house, the more rooms it has. There is some variation, but for the most part. And so where would we project this data? How do we take a picture of these houses so that they look as spaced out as possible? Well, it seems like this line would work, right? And a little aside, we're not doing linear regression. We're not trying to fit the closest line to the data. We're trying to fit the one that makes the best projection. So it's slightly different, and definitely with a different purpose. But if we do this, then we project each house to the line by drawing the perpendicular and sending it there. So we do this, and then our data set changes a little bit. It's not exactly the same one. It's not faithful to the data. But it's much simpler because now it's not 2-dimensional, it's 1-dimensional, because now we can see it like this. And now we only have one axis, which is the size feature. So now all of a sudden our data set became more simple. It went from being a 2-dimensional data set, so a table of 2 columns, to a 1-dimensional data set, so a table with only 1 column. Now every house only has 1 number attached to it, not 2. So from 2 dimensions to 1 dimension, namely size and number of rooms, to the size feature. Now, we did it from 2 dimensions to 1 dimension because it's graphically nice to see, but you can imagine that from 5 dimensions to 2 dimensions, it would be going from something like these features to the size and the location feature. So it's hard to picture 5 dimensions in our head, but imagine what we just did from 2 to 1. Imagine it doing from 5 to 2. So if you've seen statistics before, the next couple of minutes may look like a review, but I still find it interesting because I like to see things in a more geometric way. So what is the mean of a set of numbers? Well, let's say that I have 3 weights that are exactly the same and I want to balance them. So how do we balance them? How do we find the perfect point of balance for these 3 weights? And let's just assume that that bar has no weight. So what I'm going to do is I'm going to imagine that there's a wall here at the left, and I'm going to measure the distance from every point to the wall. So the one is at distance 1, then the other one's 2, and then the other one is 6. And I'm going to take the average of these points. So the mean is 1 plus 2 plus 6 divided by 3. And that's the point of equilibrium. If I were to put a balance here at 3, then the points would balance. But now there are a lot more things I can say about a set. For example, what if I have these 3 points and these 3 points? How do I tell those apart? Well, not using the mean, because they have the same mean. Notice that they balance on the same point. But if you can see, the points in the top are a lot closer to each other and the ones at the bottom are a lot more spread out. So how do I measure that? What I'm going to do is I'm going to take the distance from each point to the center. So the point in the left is a distance 1 from the center, the point in the right is a distance 1 from the center, and the point in the middle is this distance 0 from the center, because it's actually the center. It's the point where the points balance. And the same thing in the bottom, except these are 5, 5, and 0. So the variance is you're going to add these numbers, but actually it's going to square them. And the reason we square them is because actually when you take a distance that goes towards the left, you're subtracting the coordinates, and then so you're going to get a negative number. So you square everything so you get everything positive. And so for the top you get 1 squared plus 0 squared plus 1 squared divided by 3, which is 2/3. And for the bottom one we get 5 squared plus 0 squared plus 5 squared divided by 3, which is 50/3. So it's much bigger. So this is basically a measure of how spread out is a set. So now we have what is the variance of the original set. Well, from the center, the point in the left is a distance 2, the next point is a distance 1, and the point in the right is a distance 3. So the variance is 2 squared plus 1 squared plus 3 squared divided by 3, the average of these squares. And so that is 14 divided by 3. So you can see that it makes sense, 14 divided by 3, because they're kind of spread out. Now the question is, what is the variance for a 2-dimensional data set? So when the set is in the plane, what do we mean by spread out? Well, 2 things we can do is ask how spread out it is in the horizontal direction and how spread out it is in the vertical direction. So basically we forget about the height and we send everything to the horizontal or x-axis and then calculate the variance of those points, which is the x variance, and then do the same thing by forgetting the x-coordinates, sending everything to the vertical axis, and now with those points we calculate the y variance. And then we have 2 numbers, the x variance and the y variance, and they should tell us, well, how spread out is a set. However, there are some technicalities. Let's look at this set and let's look at this set. What are the x and y variances of those 2? Well, let's calculate the x variance, and let's say these distances are 2. So it's going to be 2 squared plus 0 squared plus 2 squared divided by 3, which is 8 divided by 3. And what's the y variance? Well, it's, if the distances are 1, then it's 1 squared plus 0 squared plus 1 squared divided by 3, which is 2/3. So those 2 sets have the same x variance and the same y variance, but they're fundamentally very different. So how do we tell those 2 apart? Can we have a third metric that tells us that these 2 are different? And the answer is yes, and that's going to be covariance. So the question that covariance answers is, how do we tell these 3 points apart from these 3 points? So let's think. Can you think of a number or a metric that tells those 2 sets apart? Feel free to pause the video and think about it. And I'll tell you the one that I think. It's the product of coordinates. So what if you look at the 2 numbers and multiply them, the 2 and the 1, the minus 2 and the 1, etc. Well, let's see. For the point in the middle, 0 times 0 is obviously 0. For the top right and the bottom left corner, it's actually plus 2, because 2 times 1 is 2, but minus 2 times minus 1 is also 2. And for the other 2 points is minus 2, because 2 times minus 1 is the same as minus 2 times 1, which is minus 2. So this product of coordinates is positive for these 2 points and negative for these 2 points. And it's 0 for the one in the middle, but that's okay. It still helps us tell the points apart. So basically covariance is the sum of products of coordinates. See, before it was the sum of squares of one of the coordinates. Now it's the sum of products of coordinates. So let's calculate the covariance of this set. We see that the products are minus 2, 0, and minus 2. And for this set, where the products are 2, 0, and 2. So the covariance for the set on the left is negative 2 plus 0 plus negative 2, which is minus 4 over 3, divided by 3, the average of those. And the one on the right is 2 plus 0 plus 2 divided by 3, which is 4 over 3. So the points in the left have a negative covariance, and the points in the right have a positive covariance. If you heard the term correlation, that's also very related to this. The points in the left are negatively correlated, and the ones in the right are positively correlated. Because in the ones on the left, as the x direction grows, the y direction decreases, whereas in the ones in the right, as the x direction grows, the y direction grows as well. So let's look at another set and try to calculate the covariance. This is our set. What do you think the covariance of this one is going to be? Well, let me tell you. Let's calculate all the products. They are minus 2, 0, and 2 according to this numbers over here. And then the covariance is just the sum of all those things. But you can see that they all cancel out. So the sum of all those things divided by 9, the average, is actually 0. And it made sense because this set is not positively correlated or negatively correlated. It doesn't look like a diagonal in either one of the directions. It looks like a sort of thing in the middle. So by looking at the type of set, we can sort of tell the covariance. If we have a set like this, or like this, or like this, what do you think the covariances are? So the first one looks like an inverted diagonal, so it's got negative covariance. The first one looks like it's just sort of well-centered, so it's have probably covariance of 0 or a very small covariance. And the third one has a positive covariance because it looks like a sort of forwards diagonal. So this covariance is going to help us a lot with PCA. So now we're ready to start thinking about PCA. Let's say we have a data set like this one. How do we find the perfect projection? Well, first let's put it in some coordinate axis. And the first thing we're going to do is center it. So center it means we're going to take the average of the coordinates, both in the x and in the y direction. Find that center of mass. Think of the point where this set would balance and move that to 0. So we're going to move it so that this data set is centered at 0. And now we are going to create a 2 by 2 matrix. And the 2 by 2 matrix is going to be very simple. It's just going to be formed by the two variances and the covariance of this data set. So on the top left corner, we're going to put the x variance. So the variance on the horizontal axis. In this coordinate, we're going to put the y variance. So the variance in the vertical direction. And then in the other two spots, we're going to put the covariance. We're going to put it there twice. And in the literature, this matrix is normally called sigma, but we're just going to call it the covariance matrix. And so let me just make up some numbers. This data set looks like it could have this covariance matrix 9, 4, 4, 3, because 9 is the x variance, because the data set looks like it's pretty spread in the x direction. It's not so much spread in the y direction, so the variance y is maybe something like 3. And it looks like it's has positive covariance because it looks like a forwards diagonal. So let's just say that the covariance is 4. So now we're going to do a little aside on linear transformations, because that matrix, we're going to think about it now as a linear transformation. Don't get scared with the term. Linear transformation is really just a function or a map from, say, the plane to the plane. This could be also be in higher dimensions, but here it's just going to be in 2. So it sends any point in the plane on the left to a point in the plane on the right in the following way, using the numbers of the matrix. So a point of coordinates x comma y gets sent to the point 9x plus 4y and 4x plus 3y. So two coordinates go to two coordinates, and the numbers are taken from matrix. This 9 and this 4 get encoded here at this 9x plus 4y, and this 4 and this 3 get encoded in this 4x plus 3y. If you feel more comfortable thinking of points as 2 rows instead of 2 columns, the way I did it, feel free to think of that so that you can think of matrix multiplication. But if you want to just simplify, think about it this way. So let's see what this transformation does. Let's see what it does to several points. where does the point 0, 0 go? Well, what is 9 times 0 plus 4 times 0? Well, that's just 0. And 4 times 0 plus 3 times 0, that's 0. So this goes to the point 0, 0. So let's draw the point in the left, the point 0, 0. And that goes to the point 0, 0. So very simple. Let's do another slightly more complicated point. Where do you think the point 1, 0 goes? At any moment, feel free to pause the video and think about it yourself. 1, 0 goes to 9, 4. Because if you plug in the numbers 1 and 0 for x and y, you get 9 and 4 for 9x plus 4y, because you get 9 times 1 plus 4 times 0, and then 4 times 1 plus 3 times 0. So that goes to the point 9, 4. So we're going to send the point 1, 0 in the left to the point 9, 4 at the right. And these are not drawn at scale, but I'm trying to capture the entire movement here. Next point would be 0, 1, which is over here. And you can do the math. That goes to 4, 3. So it goes over here. The next point is minus 1, 0, which is here. And it goes to minus 9, minus 4, which is over here. And finally, the point 0, minus 1, which is over here, goes to the point minus 4, 3, which is here. And hopefully you can see a pattern here, right? As a matter of fact, if you take this circle, the unit sphere, where do you think it goes? Well, it goes to this ellipse over here. Now, it almost seems like what we did was stretching the plane in a sort of diagonal direction. Actually, we did two stretchings, but one is very small. But that's really what a linear transformation does, most of them. So let's think about this. There is some vector here, the red vector, that actually goes to this one. So what happens is we sort of stretch the plane in that direction. The direction is, we can calculate in a minute, but it's 2, 1. So it's 2 units to the right and 1 unit up. That's just the direction. That's not the vector. And the magnitude is 11. We'll see why it's 11. But basically the plane got stretched by a factor of 11 in that direction. And then there's another vector which has the direction minus 1, 2. And that one gets sent to itself. So it's actually stretched by a direction of 1. Sometimes you will have different numbers, but basically think of it as 2 stretchings. And they happen to be perpendicular in this particular case. So let's see. The directions are 2, 1 and minus 1, 2. These are the eigenvectors which give us direction. And the eigenvalues, which are these factors of stretching, are 11 and 1. So those are, as I said, called eigenvalues, and they give us the magnitude. So again, we can think of a linear transformation given the eigenvectors and the eigenvalues as in the direction 2, 1, so 2 units to the right and 1 up, we stretch by 11. In the direction minus 1, 2, which is 1 unit to the left, that's minus 1, and 2 units up, we stretch by a factor of 1, so we don't do much. And so the transformation basically does this. So notice that these two vectors are very special because an average vector, so anything that goes like in this direction, for example, I'm just drawing a random vector, goes to some other thing. But the red vector goes to something that points in the same direction. And the green vector goes to something that points in the same direction. So those two are the eigenvectors. The two vectors that actually go to something that points in the same direction. Basically what you're trying to say is that the linear transformation, which is this matrix, for most vectors, it does some crazy thing. But for two particular vectors, applying it to the vector v is the same as multiplying that vector v by a number, right? So it's scaling and it's sending in the same direction. So these are the eigenvectors, the red and the green vector, and this value is the eigenvalue. So there are many ways to calculate eigenvalues and eigenvectors. My favorite was just type the matrix into Wolfram Alpha and it just tells me everything. There's an algebraic way that I won't get into much detail, but basically you take your matrix, you take the characteristic polynomial, which is subtract x minus the things in the diagonal, and then do minus for everything that's off the diagonal. Take the determinant of this, which is this formula over here, and express it as a quadratic, and factor this quadratic into two things, and then you magically get x minus 11, x minus 1. I'm going a little fast here because it's something that if you really are interested, you can read further. Then the eigenvalues are going to be the two roots of this polynomial, so 11 and 1. That's how we find the eigenvalues. And how do we find the eigenvectors? Well, now that we have the eigenvalues, then we have transformation times a vector uv, and I'm reusing the letter v, but that doesn't matter. Now we just have two coordinates, is equal to 11 times that vector, and the matrix times another vector is 1 times that vector. So if we solve these as two linear equations for u and v, we get the eigenvector 2, 1 and the eigenvector minus 1, 2. If you find this interesting and you want to see some amazing animations with amazing explanations, go to this channel, 3 Blue 1 Brown. He has a whole series on linear algebra, and his treatment of eigenvectors and eigenvalues is actually fantastic. So that may have been a little bit too much math, but think about this as the moral just says that if you have a linear transformation, it is stretching the plane in two directions. And those directions are given by the eigenvectors, and the amount you're stretching is given by the eigenvalues. Okay, so now we're ready to do PCA. First, we start with a data set and we center it. Now we calculate the covariance matrix, which as we saw, the x variance is 9, the y variance is 3, and the covariance is 4. So this matrix has eigenvectors, which give us direction, eigenvalues, which give us magnitude. The first one is direction to 1, and magnitude 11, which is this one over here. The second one is direction minus 1, 2, and magnitude 1, which is this one over here. And notice that the two eigenvectors and eigenvalues tell us a lot about our data set, right? Because it sort of tells us in what direction is spread and by how much. Also notice that the red and the green vectors are perpendicular. That's not out of luck. That's something that happens when we have a symmetric matrix. Symmetric means that in this case, this 4 and this 4 are the same. Because in general, symmetric means if you reflect the matrix over the main diagonal, you get the same matrix. So the entries on top of the diagonal are the same, and the ones below the diagonal are the corresponding one. And when the matrix is symmetric, then the eigenvectors are orthogonal or perpendicular, even in higher dimensions. Another thing that is pretty lucky is that the transformation is actually two stretchings. This also doesn't happen all the time. Some transformations are rotations or different things, and that's because sometimes the eigenvalues are imaginary numbers or complex numbers. In this case, they are real, which is also something that happens when the matrix is symmetric. So because covariance matrices are always symmetric, because that's how we built them, we put the entry on top and on the bottom. That 4, we repeated it. So in this particular case of covariance matrices, they always have very nice eigenvalues and eigenvectors that are perpendicular. So what we're gonna do is we have summarized our data set as the red vector and the green vector. And what we're gonna do is we're gonna say, okay, which one is more important? Which one do you think is more important? Well, the one with the largest eigenvalue, right? One of them matters 11 times the other one. So let's say the 11th one wins and the other one gets the boot. So we delete everything that's green and only care about what's red. And what does that mean? Well, that means we're going to consider this entire line and we're going to project everything into this line. And that is the projection. That is the picture of the data set. And let's see what we did. What we did is we turned our two-dimensional data set into this one-dimensional data set. And because we picked projecting over the eigenvector with the highest eigenvalue, that means we project over the axis that carries the most amount of information. Okay, so now we're finally ready for the big picture of PCA. Are you ready? We start with a large table of data with lots of rows and lots of columns. In this case, we're going to say 5 columns, but you're going to see how this works in general. So this gets plotted in a 5-dimensional plot. I can't draw in 5 dimensions, but this is my best sort of imaginary representation of how things would work in 5 dimensions with 5 axes. So now, from this data, we get a 5x5 covariance matrix. In the main diagonal entries, we see all the variances with respect to each of the dimensions, and in the off-diagonal entries, we get the covariance for each pair of dimensions taken at a time. And notice that this is symmetric because we put the same entry on the top right and as the bottom left. So now that we have a matrix, we calculate a bunch of eigen stuff. We calculate 5 eigenvectors with their corresponding eigenvalues. Then we order them from small to big. And now it's up to us to pick how many of the big ones do we want. That depends on the eigenvalue or on how many dimensions we want to get to. But let's say we pick the top 2 and erase the bottom 3. So now what do? We go back to our 4th-dimensional plot and plot those 2 eigenvectors with the length being the corresponding eigenvalue. So we get these 2, the red and the green. Now this creates a smaller dimensional space. In this case, it creates a plane we can see. So now what we do is we project everything with respect to this plane. So we sort of take the shadow, or like take a picture that prints in this plane, and we get a 2-dimensional plot. And this 2-dimensional plot is a pretty faithful representation of our 5-dimensional plot, because we did it the smartest possible way by picking the directions in which the data is spread the most. And therefore, from this 2-dimensional plot, we get a smaller table with 2 columns that actually captures the data as well as possible. So that's it. That's the dimensionality reduction, and that's the big picture of PCA. And that's it for this video. Thank you very much for your attention. As usual, if you like this, please subscribe for more videos coming up. Please hit like and share with your friends, and write a comment. I love to read your comments, and it's always very useful for me to see suggestions of what topics you would like to see, etc. And if you would like to tweet at me, this is my Twitter handle, Louis Likes Math. So thank you very much, and I'll see you in the next video.
Welcome to this video about partial least square regression. In this video I will give you some background to partial least square regression before we move on to see how the method works. At the end of this video we'll see how we can extract components when we use a larger dataset. Partial least square regression can be seen as an extension of the principal component regression that we covered in the previous video. I therefore recommend that you first watch the video about principal component regression so that you understand the basics. Similar to principal component regression, the method of partial least squares, also called projection to latent structures, is a technique that reduces the number of explanatory variables to a smaller set of uncorrelated variables. Both methods are used to overcome the problem with collinearity in linear regression and in cases where we have more explanatory variables than observations. Watch the lecture about principal component regression for more information. To explain how partial least square regression works, let's consider the following dataset, which is identical to the data we used in the previous lecture. This dataset consists of the three variables systolic blood pressure, cholesterol level, and age, which have been collected from 6 individuals. Suppose that we like to predict the systolic blood pressure based on the two explanatory variables cholesterol level and age. Since we have more than one explanatory variable, we will use multiple linear regression in this case. However, it is problematic to use multiple linear regression if there is a too strong correlation between the explanatory variables. A linear association between the explanatory variables is called collinearity. If we compute the Pearson correlation between the cholesterol level and age, we see that the correlation coefficient is 0.94, which is very high. This model will therefore suffer from collinearity, which means that the interpretation of the model coefficients will not be reliable because there will be an inflation in the standard errors. For example, the following two bars represent the estimated parameters of the model. We see that the estimated parameter associated with the cholesterol level is negative, whereas the estimated parameter for the age is positive, which does not make sense since the cholesterol level and age had a positive correlation. In addition, the 95% confidence intervals of the parameters in the model are very wide, which means that we cannot really trust the estimated parameters of the model. This is due to that we have collinearity in the model. One way to solve the problem with collinearity is to combine these two variables into just one variable. However, how should you combine these two variables? Remember that when we used principal component regression, these two variables were combined by using principal component analysis. If we would perform PCA on these two variables, we would end up with the following weights that represent the first eigenvector of the covariance matrix. Remember that the sum of the squared weights should be equal to 1. Based on these two weights, we can now calculate the first principal component. Based on this equation, we can compute the following values, which can be seen as the combined values of the cholesterol level and age. We then perform linear regression where the first principal component now represents our explanatory variable. However, the problem with principal component regression is that it combines the variables without involving the dependent variable. These particular weights have been optimized to achieve maximum variance of the first principal component. We see that the variable age has a higher weight, which means that more weight is put on this variable when combining the two variables to get as much variance as possible in the combined variable. However, this does not necessarily mean that this variable is better to predict the systolic blood pressure. It would make more sense to find weights that also maximize the prediction of the dependent variable. This is exactly how partial least square regression works. Partial least square regression therefore combines the two variables into one variable, which we call PLS component or latent variable. It therefore tries to find the optimal weights for alpha 1 and alpha 2, so that the combined variable both explain the dependent variable as good as possible, but also represent the explanatory variables in a good way. Similar to principal component analysis and principal component regression, partial least square regression uses the following constraint, where the sum of the squared weights should be equal to 1. To find optimal weights, different methods such as the SIM-PLS algorithm are used. How these algorithms work will not be explained in this video. Instead, I will explain how the concept works by a simple iterative example. If we solve this equation for alpha 1, we'll get the following equation. If we set alpha 2 to, for example, 0.1, we see that alpha 1 should be equal to 0.995. If we plug in these two weights in the equation, we see that we fulfill this constraint because the sum of the square weights is equal to 1, or approximately equal to 1 due to rounding effects. Let's try these weights in the following equation where we combine the two variables. To calculate the combined value for the first person based on this equation with the following weights, we plug in the cholesterol level and age of person number 1. The combined value is 129. We then do the same calculation for person number 2 and so forth. These are the combined values based on the two variables and the weights. Next, we calculate the covariance within the combined variable, the latent variable 1, LV1, and the dependent variable, which is the systolic blood pressure. The covariance between these two variables is equal to 14.14. By using these two weights, we therefore get a covariance of 14.14. Now, let's instead set alpha 2 to 0.5. If alpha 2 is equal to 0.5, alpha 1 is equal to 0.866. We should therefore combine the two variables with the following equation, which will give us the following scores. The covariance between the dependent variable and this new latent variable is 20.56. We therefore get a higher covariance when we use these weights compared to our earlier weights. Combining the two variables with these weights should therefore give a better prediction of the dependent variable. If you try a range of different values of alpha 1 between 0 and 1, we see that the value of alpha 1 that results in maximum covariance is about 0.52. The corresponding value of alpha 2 is therefore equal to about 0.85. This means that in order to get maximum covariance between the combined variable and the dependent variable, we should use the following equation. We then use this equation to calculate the scores, which represent our combined variable that has maximum covariance to the dependent variable. The reason why we want to maximize the covariance is because we then combine the variables in a way that explains both the dependent variable and the explanatory variables. We now perform linear regression, where we estimate the intercept beta 0 and the slope beta 1 with ordinary least squares. Since only 2 out of the 4 coefficients are estimated by the least square method, this explains why the method is called partial least squares. Linear regression would estimate the intercept and the slope to the following values. If we combine these two equations, we'll get the following equation that can be used for predictions. If you multiply the estimated slope with the terms inside the brackets, we'll get the final coefficients for our model. Let's illustrate the coefficients for the two explanatory variables by the following two bars. The values indicate that an increase in the cholesterol level or age increase the systolic blood pressure. We can also compute 95% confidence intervals for these parameters. Note that these 95% confidence intervals are a lot narrower compared to our original multiple linear regression model, which shows the strengths of using the PLS model when there is a presence of collinearity in the model. Standard errors and confidence intervals for a PLS model are usually obtained by some sort of iterative method. For example, one can compute a non-parametric 95% confidence interval based on many bootstrap samples. Once we have established our partial least square regression equation, we can use it for prediction. For example, let's say that we like to predict the systolic blood pressure of a person with a cholesterol level of 125 and an age of 40. We plug in the values in the equation and do the math. We see that the predicted systolic blood pressure for this person is 121. Now, let's have a look at an example where we have 4 explanatory variables. In addition to the cholesterol level and age, we now also have measurements of body weight in kilos and body height in centimeters of the 6 individuals. When we have 4 explanatory variables, we'll get 4 components. To know how many of these we should extract, we could perform cross-validation to calculate the so-called root mean squared error of prediction. If we have plenty of data, we could use a validation dataset, but since we here only have 60 individuals, we'll perform the leave-one-out cross-validation to calculate the root mean squared error of prediction. This means that we should generate a PLS model based on all data points except the first individual, which is left out. We then use the PLS model to estimate the systolic blood pressure based on the explanatory variables for the person that was left out. We compute this for a PLS model including either 0, 1, 2 or 3 components. We then plug in the true systolic blood pressure for person number 1. We can then calculate how far away the prediction is from the true value for all types of models that extracted either 0, 1, 2 or 3 components. Next, we compute the PLS model based on person number 1, 3, 4, 5 and 6, where we leave out the second individual. Then we predict the systolic blood pressure of person number 2 and compare with the observed value. Once we have left out all individuals, we'll have 6 residuals. If you take the square root of the mean of the sum of the squared residuals, where n is the sample size, which is 6 in this example, we'll get the following table that shows the root mean squared error of prediction for the different number of extracted components. A model with no extracted components corresponds to a model with only an intercept. We can see that the model based on 2 principal components results in the lowest root mean squared error of prediction. The following plot shows how the root mean squared error of prediction changes as a function of different number of components. By using 2 components instead of just 1, the error is clearly reduced. Whereas more components increase the error, we should aim to use as few components as possible that result in as small error as possible. If we would, for example, extract all components, the use of the partial least square regression would not make sense, because we will then not reduce the number of parameters that are estimated by the least square method. Suppose that we decide to extract 2 components. Then our partial least square regression model now looks like this. The 2 latent variables have the following weights associated with the 4 variables. If we fit a linear model with the 2 latent variables, we'll get the following model with 3 estimated parameters. If we plug in the equations for LV1 and LV2, we'll get the following equation. After some math, we'll have our final linear model with the following coefficients. We can then compute 95% confidence intervals for these parameters and use the model for prediction. This was the end of this lecture about partial least square regression. In the next lecture, we'll have a look at partial least square discriminant analysis, which can be used for classification. Thanks for watching.